Hello and welcome to Aditya classes, where these days we have been studying Simplex. Now, in linear programming, we learned how to formulate a linear problem. Then we learned how to solve a linear problem having only two variables using graphical method. Then whenever you have more than two variables, you cannot solve that problem using graphical method. So we moved on to the Simplex method. And in Simplex method, up till this point we have covered all kinds of problems, straightforward problems, all kind of straightforward formulations. Now we'll see certain special cases, certain shortcuts if possible. Generally, personally, I do not prefer shortcuts, because if you start taking shortcuts, there can be thousands of different shortcuts. So I always recommend my students that they should have their basics very clear. If those basics are very clear, then you can solve the Simplex as it is within 10-15 minutes. So that is the idea, but here we'll see certain special cases and if possible certain obvious shortcuts, which will not exactly be shortcuts, which will be kind of reformulation of the problem. So this is what we'll be studying these days in today's lecture and in some lectures to come. So for the purpose, we are taking a formulation over here. Now if we have a look at this formulation, we have three variables x1, x2 and x3, and there are four constraints. We have first constraint, second constraint, third constraint and fourth constraint. So we have four constraints. There are four constraints, three variables, and then one of them is of type greater than, one of them is of type equal. The objective function is minimize. Now this problem has all possible type of constraints, all possible type of inequalities. If we just try to have a look into this problem, what will be the size of Simplex problem, what will be the amount of calculations in this Simplex problem, we see that roughly my table would be like this. I will be having x1, x2, x3. Then there will be first constraint, second constraint, third constraint, fourth constraint. So I will be having 4 rows. And then these two will be having slack variables. This will be having a surplus variable, surplus with an artificial. So I will be having S1, S2, S3. And this will also create not S1, S2, S3, let me call them S2, S3, S4, because it is second, third and fourth constraint. And then there will be an artificial for greater than. So it will be A3. And this is one more equation. For these, we'll look in a bit. We make use of artificial variables. We have not talked of this as yet. What do we do with the equal type constraints? We make use of artificial variable. We'll check it in a bit. But the idea is this will be the size of my table. How many elements are there in this table? 1, 2, 3, 4, 5, 6, 7, 8. 8 multiplied by 4. There are 32 elements. So whenever you are making a switch from one table to another table, you will be operating upon 32 different calculations. You will be working on 32 different calculations whenever you are switching from first initial Simplex table to second iteration to third iteration to fourth iteration, so long as we do not get our best results. Yes, it might not be 32 each time, because if an artificial variable goes out, we will reject it. But the idea is, look at the magnitude of the starting point, 32 calculations. Now, first thing that we are learning over here is, we have a new kind of inequality which is of type equal. We have a new type of constraint which is of type equal. x1 plus x2 plus x3 is equal to 100. Now, if we talk of this constraint, what do you do with this? x1, this is less than, so you add a slack. And this being second, let me put a x2, s2. x1 plus s2 is equal to 20. What do you do with this one? You make it x2. Now this is greater than 30, so I need to deduct something. If I deduct something, it becomes a negative starting point. So I put an artificial variable and making it equal to 30. This is how we conventionally start this kind of solution, this kind of formulation. This is less than, so I'll put a slack, that is S4 is equal to 40. So this is how conventionally I would have solved these, converted these this canonical form into standard form. This is how conventionally I might have approached. Today we'll be seeing something different. This is how I might have dealt with them. And what about equality kind of constraints? This is the first time we are getting an equality kind of constraint. What do we do with these? Now if you remember, when I go for IBFS, what is the rule that we have studied up till this point? That all decision variables and slack variables equal to 0. We put all decisions, sorry, not slack, surplus. Up till this point we have learned that all decision variables and surplus variables are put equal to 0 in order to reach IBFS. Now if I put all decision variables and surplus variables 0, decision 0, so x1 is 0, x2 is 0, x3 is 0, decisions are 0, surplus are 0, so this is also 0 because this is surplus. So my IBFS from this would be decision 0 giving me S2 is equal to 20. Decision and surplus 0 giving me A3 is equal to 30. Decision 0 giving me S4 is equal to 40. This is how conventionally I would have converted this canonical into standard and then gone about my IBFS. This was canonical, this is standard, this is IBFS. Standard form. This would have been my IBFS for these three. And what about this? This is also a constraint. Now if I put all decision variables equal to 0, this will make it 0 plus 0 plus 0 is equal to 100, which is very incorrect. So what do we do in case of equalities? We start them also with an artificial variable. Thereby giving me IBFS of A1 is equal to 100, because you will put decision variables equal to 0, your IBFS will become A1 is equal to 100. So this becomes my IBFS. This is the conventional way of going about it. Fine. What is the conventional way? These three inequalities, these three constraints we can deal with. We are practiced with them. This is a new kind of constraint which is of type equality. If I put all decision variables 0, then it gives me a false start. 0 is equal to 100, which is very incorrect. So what I do is I make use of artificial variable once again. What is artificial variable? I do not know. In earlier lectures also we have seen that I have no clue what artificial variable is. But artificial variable is some kind of arrangement, some kind of variable that gives me a starting point. So once I have that starting point, I can proceed. Here also we have our starting point as A3 is equal to 30, and then we saw that whenever A3 is outgoing variable, we remove it from our further calculations. Remember, whenever we have an incoming variable and it replaces an outgoing variable, if A3 becomes outgoing variable, I never talk of A3 thereafter. Same will be with A1. This is the rule, that whenever an artificial variable becomes an outgoing variable, we do not talk of that variable from that point onwards. This is the rule. So the idea is, I again make use of some artificial variable. I have no clue what it is, but I make use of this artificial variable to get me a start. So this is conventional way. Conventionally, this was your linear formulation. This is conversion into standard form. This is IBFS. And then you can get on with your simplex solution. Now, a new arrangement, an alternative arrangement that we are learning today, that we are seeing today is, this will start with an artificial variable, these two will start with slack variables. This will again start with a surplus variable and an artificial variable. So what I'll do is, I'll pick up this constraint. What is this constraint? This constraint is x2 greater than equal to 30. x2 is greater than 30. At most it can be equal, but it is greater than 30. So can I say that x2 is something more than 30? In case x2 is equal to 30, a will become 0. In case x2 is, let's say, 35, a will take a value of 5. In case x2 is 50, a will take a value of 20. In case x2 is equal to 30, a will take a value of 0. So the idea is this constraint can be written as this also. x2 greater than 30 can definitely be written as x2 is equal to 30 plus a. Now what I'll do is, I already have value of x2, right? I already have value of x2 in some terms, but I already have a value of x2. I'll substitute this value of x2 in complete question. What happens? Substituting x2 is equal to 30 plus a. I'll be substituting x2 is equal to 30 plus a. Now I hope you understand why are we substituting as 30 plus a as a consequence of this constraint. Now let us see what our formulation becomes. x2 is equal to 30 plus a. We have an x2 over here. Our objective function will become zmin is equal to 5x1 plus 4x2. In place of x2, this time I am putting 30 plus a plus 3x3, thereby making it 5x1 plus 4a plus 3x3 plus 120. When you are exactly solving a linear problem for minimization or maximization, these constants do not play a role, because these constants will be there, whatever your decision is. Whatever your decision about x1, x2, x3, a, b, c, whatever your decision about these variables is, you may have it. But this offset of 120 will always remain there. So while solving a linear problem using simplex, we tend to ignore these constants. It will remain here, it will be here, but we will ignore it for the sake of solution using simplex, for simplex formulation. Now, zmin has been translated, zmin has been converted. Fine. So zmin, which looked like 5x1 plus 4x2 plus 3x3, now I say it is 5x1 plus 4a plus 3x3, and this 4a has a constant addition of 120 also. What about this? This will become x1 plus, instead of x2 I am writing 30 plus a plus x3 is equal to 100, thereby making it x1 plus a plus x3 is equal to 100 minus 30, making it 70. This becomes my first constraint. This is my objective function. I have my objective function, I have my first constraint. Second constraint x1, there is no x2, so there is no substitution. We have x1 is equal to less than equal to 20, being my second constraint. Third constraint you need not write down, because this was saying that x2 should be greater than 30. I already know the value of x2. Value of x2 is 30 plus a. So we can ignore this constraint safely. What has happened? One is I have removed one constraint. Second is I have removed an artificial variable, thereby making my simplex problem much more smaller. We'll compare it right now. In any case, first one is x1 less than 20, second is gone because second is already solved, because I know the value of it, 30 plus a. Third one is x3 less than 40. So instead of 4 constraints, now I'll be working with 3 constraints. And if I look at the solution of this problem, earlier I was having x1, x2, x3, s1, no, it was not s1, it was s2 for this, s3, s2, s3, s4, then there was an a1 and a3, thereby making it 1, 2, 3, 4, 5, 6, 7, 8 variables, and then there were 4 constraints. So I would have had 1, 2, 3, 4, thereby making it a simplex of 32 different cells, a matrix of 32 different cells, a transfer from first table to second table of 32 calculations. 32 calculations would have transferred your first table to second table. Now let's just compare what is the scenario. First thing is I have only 3 constraints. And what are the variables? Variables are x1, x2 is almost gone from my formulation. There is no x2 in my formulation, rather I have an a. So the solution would be x1, a, x3, x1, a, x3. As far as slacks are concerned, there will be s2 and s3, s2 and s3. As far as artificial variables are concerned, I will be having only one artificial variable over here. These are slacks, so there will be no artificial variable. So I will be having only a1. And we will see, I will even be removing this a1. For now, let us say this is my problem. And now I have 3 constraints, 1, 2 and 3. Now look at the scenario. You were having 32 calculations per transfer of one table to second table. This time I have 1, 2, 3, 4, 5, 6, 6 into 3, 18. So from where are we getting this power? Where are we getting this power from? Just a tiny little substitution, a smart little substitution of x2 is equal to 30 plus a has brought me down from 32 calculations per transfer to 18 calculations. And just wait for some moment, I will be reducing this 18 further down to 15. But just to put things in perspective, just to think over it, just to ponder over it, that why are we making this substitution? Why are we not going ahead and solving it directly? This is why we are making this substitution. Now, as an assignment, what you can do is you can solve this simplex problem directly the way we do. You can solve it directly. I'll put up a standard form of this problem for direct solution. You can do that calculation. I'll be making use of these certain new tools, these certain new faster mechanisms. So this is the idea. From 32 we are down to 18. In original solution there would have been 32 transformations each time. This time we will be having 18 transformations only. Now, once we have transformed our given problem into a different problem through one substitution, once we have transformed our 4 constraints into 3 constraints, now let us get on with our task of solving it. Fine. How do we solve it? We should convert it into standard form. Standard form would be first constraint. First constraint is we need to convert all inequalities into equalities. This is as it is equality. So we'll call it x1 plus a plus x3 is equal to 70. Second one would become x1. This is less than, so we'll make use of a slack. S1 is equal to 20. x3 plus s2 is equal to 40. So we have all 3 constraints over here. One was as it is equality, so we have left it unaltered. Other 2 were less than type of inequality, so I have converted them into equalities. And as a result of this conversion of canonical into standard, I have certain new variables. Those new variables would be incorporated into Zmin also. to get 5x1 plus 4a plus 3x3 plus 2 slack variables 0 into S1 plus 0 into S2 plus there is a constant of 120 also. So this becomes my conversion of canonical into standard. Next, once we have our standard form, we can go into for IBFS. What will be my IBFS? My IBFS would be, from here I will get S1 is equal to 20, here I will get S2 is equal to 40, and here, as I told earlier, for equality type of constraints, if it were like this, x1 plus x2 plus x3 is equal to 40. In order to get IBFS from this, if I put all decision variables equal to 0, it will make 0 is equal to 40. How do we avoid this kind of situation? We avoid this kind of situation by making use of an artificial variable. Then, if you put all decision variables 0, still you are left with a1 is equal to 40 to give you IBFS of a1 is equal to 40. So, conventionally, when you have equality kind of constraints, you make start with artificial variable. But in this case, I am not even using this artificial variable because I already have some new variable, some other variable a. I cannot touch x1, x2 and x3 because these are the decision variables. But I have made a substitution and now I can make use of a. So, I will start with putting decision variables equal to 0. So, x1 and x3 will be 0 and a will become 70. So, this is our second thing that we have done differently this time. First thing that we did differently was making a substitution. Second thing that we are doing differently is we should have made use of an artificial variable, but because I already have a new variable over here other than decision variables. See, the rule is putting decision variables and surplus variables 0. Fine. The rule is decision and surplus should be made equal to 0. I am making decision 0. If there were a surplus, I would have made it 0. There is no rule for any other variable. So, the rule applies to decision and surplus. I put decision equal to 0, but still I am not getting into this kind of situation 0 is equal to 40 because this time I am getting a is equal to 70. So, this is an acceptable IBFS, a is equal to 70. I am not getting this kind of mathematical error. So, I will start with this point, fine. So, my IBFS would be a is equal to 70, S1 is equal to 20 and S2 is equal to 40. Now, let me have my we will be having b and theta. What about objective function? We have x1, a, x3, s1, s2. Constant we will not be touching because constant will remain there. All you need to do is optimize upon your variables because constant component will always remain constant. You cannot change it. So, I will be having 5 variables, that is s1, s2, s1 and s2, x3. Instead of x2, I am having a and then there is x1. Fine. Their contributions are 5, 4, 3, 0, 0. 5, 4, 3, 0 and 0. IBFS is a is equal to 70. You can see that everything is same as we have always done with the exception of 2 new things that we tried over here. And you can already see that a situation where I was making use of 32 calculations to move from one table to another. Now, I will be making use of 1, 2, 3, 4, 5, 15. Instead of 32, I am down to 15, less than half. 32 calculations we needed here, we checked earlier. Now, I will be needing 15 calculations to move from one table to another. So, in half calculations, I will be moving from one table to another. This is the power of this substitution and this logic. That why make use of an artificial variable? The rule says decision variables and surplus should be 0. I have made decision 0. If there were a surplus, I would have made it 0. But I avoided the surplus over here. I avoided the artificial over here. and hence I'm down to 15 calculations. Now what are the constraints? What are their contributions? A is contributing 4, 0 and 0. The constraints are over here. We have a 1, 1, 1. This is an A. This looks like a 9. 1, 1, 1, 0 and 0. This will be 1, 0, 0, 1. Then we have x1 is equal to 1. And then we have x3 is equal to 1 from this constraint. x3 is 1, s2 is 1. x3 is 1, s2 is 1. And s2 is equal to 40 is my IBFS from this constraint. This is my initial simplex table. Now, I have Cj, let me find out Zj, and this being a case of minimization, my net evaluation row will be Zj minus Cj. What about Zj? Zj is sum product of every column respectively with its contribution. Column with respectively with contribution. So, when you multiply this column to these contributions, second row will always be multiplied to 0 at some point. This will be multiplied to 0. So, technically, second and third row will not be participating in sum, the sum total that we are taking by multiplying each column with contribution. So, these two will become 0. Ultimately, I will be getting my values only from this row. It will be 4 into 1 plus 0 plus 0. 4 into 1 plus 0 plus 0. 4 into 1. Then I need Zj minus Cj. 4 minus 5. 4 minus 3 is 1. I have maximum positive. There are 3 zeros, then there is a minus 1. So, maximum positive is this. Let us find out theta. Theta is B divided by key column. This is our key column. If we divide theta by key column, 70 by 1, 70, 20 by 0, infinite, 40 by 1, 40. This gives me my key row. So, I have this as key row and this becomes your key element. Fine. Can I take this data to? I'll make use of this color. Table 1. Can I transfer this data to second table? We'll make it here itself. This time we are having small tables. x1, A, x3, s1, s2, b and theta. Contributions being 5, 4, 3, 0 and 0. Now, incoming variable is x3, outgoing variable is s2. Key row is s2, so it is going out. So, these two are still there, A and S1. S2 is being replaced by X3. So, I will get X3 over here. Then contributions, A is contributing me with 4, X3 is contributing 3. Now, I need to bring in all the values over here. What are the rules? The rules are for key row, divide all elements by key element. Then there is another rule for all other rows. For this, I will be making use of this rule, key row rule. Then there are two other rows. For them, the rule is old row I minus key column element I multiplied by modified key row is equal to new row I. These are our two rules. So, divide complete key row by key element. Key element is 1. So, when you divide all elements by 1, there will be no change. So, I can directly write them over here 0, 0, 1, 0, 1 and 40. Done. Key row has been transferred. What about other rows? Let me talk of first row. Old row 1. Old row 1 minus key column element 1 multiplied by modified key row is equal to new row 1. Old row 1 is 1, 1, 1, 0, 0 and 70. Fine. Key column element 1. key column element 1, it is 1 multiplied by modified key row we have over here 0 0 1 0 1 40, giving me values of 1 1 0 0 minus 1 30, giving me values of 1 1 0 0 minus 1 and 30. These are the values. Then let us bring on second row also. Key column element will change, modified key row will remain same. What is our second row? It is 1 0 0 1 0 1 0 0 1 0 and last one is 20. Old row, this time we are not talking of 1, rather we are talking of old row 2, key column element 2, new row 2. 1 0 0 1 0 and 20. Key column element 2, key column element 2 is 0. We have zeros over here. And then modified key row is 0 0 1 0 1 40. 0 0 1 0 1 40. 1 minus 0 would give me a 1 0 0 1 0 20 minus 40 would give me a minus 20. Sorry, this will become 0. So it will be 20. So what do I get? I get 1 0 0 1 0 and 20. If you see, we get the same row once again. Why are we getting same row? Because the key column element was 0, key column element is 0, thereby making this term completely irrelevant because everything is multiplied to 0. So old row is equal to new row. In any case, we have found it, we have determined it. Let us find out our Zj and then Zj minus Cj. Zj would be 4 multiplied by 1. All these will be multiplied to 0 at some point of time, so they will be irrelevant. First row and third row will be participating in total. 4 plus 0, 4 plus 0, 0 plus 3, 0 plus 0, minus 4 plus 3, minus 1. Then we have Zj minus Cj, 4 minus 5, minus 1, 0, 0, 0, Zj minus Cj, minus 1. Everything is either 0 or negative. So we can stop at this point and we can say that this is my final solution. What will be my final solution? Can I try to summarize it over here? My final solution is this is our table 2. Okay, final solution is A is equal to 30. A is equal to 30, thereby making x2 is equal to, implies x2 is equal to 30 plus A, 30 plus 30. So x2 is equal to 60. x1 is not in this list, so x1 is 0 and x3 is 40. x3 is 40. So this is my solution. x1, x3 and x2 is 60, giving me z minimum of, what will be value of z minimum? 543. 5x1 plus 4x2 plus 3x3. Now I have values of x1, x2, x3. Yes, I was getting a value of A, but A was my substitution. Ultimately, the linear problem wanted a solution in terms of x1, x2, x3. So I am coming back to my first problem, initial problem that was given in the question. What will be z min? 5 into 0 would make it a 0. 4 into x2, 4 into x2, 4 into 60 plus 3 into 40, making it 0 plus 240 plus 120. Z min is equal to 360. x1 is equal to 0, x2 is equal to 60, x3 is equal to 40. This is my final solution for this. Now I do understand that this lecture was a bit lengthy one, but if we look at the calculations, you can see how easy the calculations have been. Everything was 1, 0, all the calculations were very simple. Instead of 32 operations per transfer of a matrix, I was down to 15 calculations per transformation, just by this tiny little understanding that wherever you are getting this kind of constraint, this particular kind of constraint, yes, you can do it with less than type of constraints also, but why touch a less than type constraint? Because less than type constraint as it is will get only a slack variable. The problem is with greater than constraints, because greater than constraints take you into surplus zone, surplus will take you into artificial variable will take you into M will further create calculation issues. So the idea is, in order to avoid surplus variables, in order to avoid artificial variables, in order to avoid either big M or two-phase method, what I have done is, if I have this kind of constraint, specifically this kind of constraint where one variable is greater than something, if you have this kind of constraint, you can make use of this kind of substitution, and thereby forgetting this, because you already have solved this constraint in terms of some other variable. And what this does is, this also saves us in equality, where otherwise I would have made use of an artificial variable, but this time I got away by putting just decision variables equal to 0 and getting my IBFS as A is equal to 70. If it were an x2, I would have had x1 plus x2 plus x3 is equal to 70, 0 plus 0 plus 0 is equal to 70, and in order to avoid this thing, I would have added an A1 over here. This time I got away with A1 also. So this is the idea behind this particular kind of formulation, where you have this kind of constraint. If ever you come across this kind of constraint with one variable and greater than kind of inequality, you can make a substitution. Fine. You can even make these substitutions for less than type, but they won't be that much beneficial. Greater than type is definitely very beneficial for us. And we'll take a new question in next lecture, where we'll have a different kind of formulation and we'll see how we can make use of these tricks that we have learned in this particular lecture. So if there are certain questions, certain confusions, you can either leave them in the comment box, or you can watch the next video, because there again I'll be taking a similar kind of problem, and then again I'll be making use of these learnings that I have developed in this particular lecture. So probably you might be able to practice more. So this was it. I remember. This is how I solved this using our new mechanism of making substitutions. I told you that I'll give you a formulation or a standard form of this, so that you can solve it for practice sake using our old method. So I'll give you a standard form of this. What will be the standard form of this? If I make use of some other color, the standard form will be x1 plus x2 plus x3 plus a1 is equal to 100, x1 plus s1 is equal to 20, x2 minus s2 plus a2 is equal to 30. This is our second constraint, na? So let us make it 2, let us make it 3. And last one would have been x3 plus s4 is equal to 40. I have converted all these constraints into equalities. The canonical form has been converted into standard form. This is the conventional way we do these problems. So you can try for your sake using this method, the conventional method, where this is the standard form. And what about the objective function? Objective function would become zmin 5, 4 and 3. 5x1 plus 4x2 plus 3 x3. Then there is s2, s3, s4 plus 0 s2 plus 0 s3 plus 0 s4. Then there are two artificial variables. It is minimization. So artificial variable gets multiplied to plus m. I am using big M method. So it will be plus m a1 plus m a2. We called it a2, we called it a3. So this would have been our standard form of this given problem, which you would have solved the conventional way that we have studied. But today what we have learnt is, if you have this kind of constraint, greater than kind of constraint with one variable, you can make a substitution. What this substitution does is, first is it removes this constraint. Second is, if at all there are some equality kind of constraints, you are saved with your artificial variable. You can get away without making use of artificial variable. We are just starting with a is equal to 70 and the result is over here. Instead of having such a big contribution function, I am down to such a small contribution function. A contribution function with 1, 2, 3, 4, 5, 6, 7 and 8 variables. I am down to 5 variables. A table with 4 constraints. First constraint, second constraint, third constraint and fourth constraint. I am down to 3 constraints. Either ways, we will get the same answers. If you solve it using conventional learnings that we have developed, you will also get this answer. But this is how we can make use of this shortcut. So this was it for our today's lecture. In the coming lecture, we will take up a special question that was suggested by a learner from our channel. And because that question was formulated in such a way that its formulation will come down to this kind of formulation. That's why I opened this particular special way. That this is a special case where we can make use of this technique, and in next lecture we will talk about that question. So this was it for our today's lecture. Thanks for watching. Bye bye. Take care.